It's time for everybody's favorite, graphs as functions. It's so excited that there's an indent right here in my notes. So we talked about functions in tables. We talked about solving and evaluating functions. Now, how can functions appear as graphs? Well, inputs, those are often called x, and they're often the horizontal aspect of a graph, okay? Outputs are often called y. Not always, right? We've done a lot of things. Here the output was q. Here the output was output. Here the output was d, right? It doesn't have to be y. It's just very normal. So it's important to label your axes. A lot of times it's x and y, but not always. All right, if we had m and d, we'd write m and d right here. All right, and then we also need some sense of scale. So a lot of times if we're just counting by one, you don't have to necessarily label everyone, but you can just kind of go 1, 2, 3, 4, 5 and just say, okay, this is the 5 mark. And it doesn't have to be the same for the x's and the y's. So if we wanted to, we could have each box be 1 for the x-axis and each box be 2 for the y-axis. It just depends on what kind of data we're looking at so we can make it fit. Okay. And again, we can have any point that we want here. It just can be written as a point with the x-coordinate first and then the y-coordinate inside parentheses. So the x-coordinate is we say, okay, what's the x value down here? X value down there is 3. So the x-coordinate of this point is 3. And then look up here, what's the y-coordinate? It's not 4, remember, because in the y's we're counting by 2. The y-coordinate is 8, where it crosses that y-axis. Okay, so this is the point 3, 8. And we can talk about functions. So a graph of a function is just all the points that make that function true. A graph of a function is all of the points. So here, right, y is a function of x. X, in this case, can be infinitely many things. And each x is going to have a certain y. This first one's a cubic function. The second one's a line. The third one's a circle. Okay? Infinitely many inputs and infinitely many outputs. So tables don't really make sense here. If you tried to do a table with infinitely many inputs and outputs, well, you'd be there for a while. Nobody wants to do that. So specifically here, we're curious about functions. Function means if I give you an input, there's exactly one output. So let's look at any value of x and say, how many values of y are there? Let's change colors to orange. Let's look at this first graph. Okay. Let's just pick an x. If I look at an x value of 1, look up and down. Oh, there's only one output with an input of 1. Look at, -2, right? Look all the way up and all the way down. How many times is there an output of, or how many times is there a graph that has an output for that input of -2? Well, only one. This is the only point on the graph with an x value of -2. And we can do this for all the points. And every single point, you search up and down and say, okay, well, where are all the places on this graph with that input? And there's only going to be one. Same with the second function. At any x-coordinate, pick any x-coordinate you want. You look up and down at that x-coordinate, you're only going to have one possible y-coordinate. It only crosses the graph once. So at the x value of 2, the y value in this case is also 2. Right? This is the point 2, 2. This is the point 1, -3, and so on. There's never going to be another point with the same x-coordinate and a different y-coordinate. If there were, right, it would look like 1, something. The x-coordinate would be here, but there's no other graph to give us another y-coordinate over here, you know? The difference is, of course, over here. If I look at an x value of 1 and say, how many points on this graph have an x value of 1? Well, we could look up to find this point on the graph with an x value of 1, and we could look down to find this point on the graph as an x value of 1. So there are 2 points on this graph. I don't know what number this is. Let's approximate it as like 2.8. There are 2 points on this graph that have the same x coordinate. This one's not a function. The other two are functions for that reason. And that's kind of the behind the scenes things. Most people learn this vertical line test, which we kind of did when we were looking at that. The vertical line test is just a way to tell graphically whether an output is a function of its input. So you can think about drawing vertical lines through a graph, and if any of those vertical lines crosses the graph more than once, then the graph does not define a function. So again, let's draw some lines. On this first one, any vertical line we draw, only crossing the graph once, right? All of these vertical lines I'm drawing, only crossing the blue once. Same for the second graph. And while in the third graph, there's a line that only crosses it once, if we draw a bunch of vertical lines, we're going to notice, oh man, a lot of these vertical lines are crossing the blue graph more than once. All there has to be is one vertical line. It only takes one to fail. Whew. Kind of dark. But yeah, that's another way of seeing functionality. And whoa, just went black there for a second. Look at example 9. Given the first graph and example, let's go back to this graph. Evaluate f of 1. So again, evaluate, that was from the last video. Says, I give you an input, and I'm curious what the output is. So what we do is we find x equals 1, input of 1 over on this graph. All right, so these are all the points. These are all the points that have an input of 1. What's the output? The output is where we are at the function. So that's only that orange point that we drew earlier, right? We're saying, where is this function when x is 1? And the function's only in one spot. Because it's a function, it can only be in one spot if it's a function. So it's only happening at that orange dot. So we know that f of 1, I'm not going to change the colors back. F of 1 is that y value of -3. The x value is 1, y value is -3. And we can do part B. Solve, okay, so solve gives us the output and wants us to find the input. So for that same graph, if we're having an output of 3, what is the input going to be? So this is going to be similar. Look at all the points that have an output of 3. All the points that have a y value of 3. And in this case, there are 2 points on the graph that have that y value of 3. What are the points? Not quite at -1. It's approximately like -1.2 or something. It's kind of hard to see. And this one's like a little bit more than 2. Maybe it's 2.2. So there are 2 inputs here that give us that output. So this is going to be true when x is approximately equal to -1.2 and 2.2. In this notation right here, this means approximately equal to. Like a wavy equals sign. All right, and that's all the information for this video. Stick around if you want to try it now. Do this example again, A and B. Again, f of 1. Right, evaluate f of 1 and solve f of x equals 3. For example 9, or with the second graph. Do it again now with this graph. So go ahead and do it now. See if you get the right answer. All right. So what is f of 1? Again, that's an input of 1 on the second graph. An input of 1 is going to be everything over here. There's only one point that has it. What is that point? Looks about to be 2.5. The point 1, comma 2.5 about. That's what we'll write here. You could use the approximately equal sign. I know it's exactly 2.5 in this case, so that's why I'm doing it. And then when is this function equal to 3? Well, it's asking when is there a y value of 3? In this case, there's only a y value of 3 once. That's right here when x is 0. This is the point 0, comma 3. That's going to be the answer when x is 0. That's the solution to this try it now. Let me know if you have any questions. And until next time, which will be 1.1.6. Bye-bye.